So what does it say? How many photons are produced in a laser pulse of 0.385 joules at 499 nanometers? Okay, so this now, let's see, what is this? This is, what would you call this? Light and energy. That's 230. Yeah, so we could go over, these are different equations that you'll use to solve these problems in this module.
Okay.
So, let me see, I don't have my book, but...
I have it with me.
Oh, perfect, yeah, so here has the equations. And see, I think I can remember them. So your wavelength, they do this fancy little letter for wavelength. How does it go? Yeah, wavelength times your frequency equals the speed of sound. That's a constant. So C is always 2.99, I guess. Well, 3 times 10 to the 8th meters per second. Your wavelength, that will be, usually they give it to you in meters, but you need to convert it to meters. And then frequency is 1 over seconds. Those are your units.
So that's the volume?
Frequency.
Oh, frequency.
Yeah, it's a little cursive V. It has a little lip on it.
Frequency.
Yep.
Frequency. And C is?
Speed is sound.
Speed of sound, right?
Yep. And C, that's what it equals right up here. 3 times 10 to the 8th meters per second.
And how's it at one fifth?
1 over seconds.
1 over second?
Yeah, so that's the units. V will always be like 5 1 over seconds. Instead of like 5 seconds, it's 1 over seconds. So that you don't really need to know. They also call it hertz. So hertz.
Hertz? Oh.
Yeah, you'll see that in the book.
Okay.
And then the next equation is your energy equals frequency times h. And h is, let me write it up here. H equals, it's Planck's constant. I think it's 6.626 times 10 to the negative 34th. But I'll let check because I haven't looked at it in a while. Yeah, so this is module 4. This isn't quite unit 2. I can grab it. It's just right here.
Okay.
I'll be right back. So here we go.
I thought it was your book.
Yep, this is my book.
Oh.
So unit 2.
Oh, that was unit 2 over here.
Yep.
Section.
So Planck's constant, where are you? H, 6.26 times 10 to the negative 34 joules per second. Okay. So now,
Is that G?
yeah, joules per second.
Okay.
And E is energy. So we'll use these two equations to solve this.
Okay. So we use that formula?
Yeah, we'll need them both actually. So it says how many photons are produced in a laser pulse of So we have 0.385 joules and 499 nanometers. Nanometers. Okie doke. So joules, let's see, I used to have a thing on 5 meters, 5.2 meters per second. Yeah, okay. So what you'll do is you'll take this number, plug it into here, and you'll solve for V. So we'll rewrite this equation as V equals, we divide both sides by this little upside down y, which is wavelength. So it would be V equals C over lambda. So then we plug in our units, it's 3 times 10 to the 8th divided by, and our wavelength, we have to convert nanometers to meters.
Okay, so meters, so we divide it?
Yeah, so an easy way that I find to do it is just go 499 times 10 to the negative 9th.
How's it negative on 9th?
Because 1 meter equals 1 times 10 to the negative 9th nanometers.
Oh, okay, I remember that. I see. Okay.
So then we just times 499 by 1 times 10 to the negative 9th, and we get 499 times 10 to the negative 9th.
Nice. It's very interesting. Glad chemistry has a lot of math.
Yeah, it does.
Yeah.
And these, when you put them in your calculator, you'll need to put them in parentheses.
Never forget those.
Yeah. So let's see what that equals.
.01 times by the power of 14.
Yep. Okay, so that's our V. Our next step will be to plug in V right here to find our energy.
Okay, so we plug that one there, okay.
Yep, and H is this guy.
That's the, oh man, the professor's name, it's the formula.
Yeah, Planck's constant.
Planck's constant, okay.
Yep. So our E equals, parentheses, 6.01 times 10 to the 14th times H, which is 6.626 times 10 to the negative 34th.
Question.
Yeah.
After you solve this, does it have to be into 2 digits or longer?
Yeah, I would just leave it to 2 digits. I wouldn't worry about keeping too many.
Okay.
Just 2 is fine. The 100th place.
Oh, okay.
You got 3.98?
Yep.
Okay, 3.98, and it's times 10 to the negative 19th. And the units on that are joules, but they're joules per photon.
per
Photon. Yep. Photon is just a little particle of light.
Okay.
So joules per particle of light. So now what we have to do to find out how many photons are in a pulse of 0.385 joules is divide by joules. So the joules cancel. And I can't remember if we divide, let's see, because that over that, this is joules over 1. Yeah, so then we take, so number of photons, which is what it's asking for, equals 0.385 divided by 3.98 times 10 to the negative 19th. And since that's joules, and this is joules per photon, the units cancel to be photons.
So you cross them out and the proton along, right?
Yeah, let me make sure, because that's joules times photons over 1 times joules. Yeah, so it's photons over 1. Yep, so our units are right. So let's see.
Oops. Do we have to put that in parentheses too?
Yeah, that will be in parentheses.
Mine says 9.67.
Oh, we could round 9.67.
So that's the answer of number of photons?
Yep,
I mean
photons.
photons.
Yeah, photons, protons, they both sound almost the same.
Yeah.
Yeah, so we use both those equations. So you'll use these two equations a lot, that one and this one. And you'll just solve for different variables. We solved for V in this case. You can solve for lambda, which is wavelength. And so, yeah.
Okay, so that 140 and 499 is the wavelength, right?
Yep, that was our wavelength. And we converted it to nanometers just by using 10 to the negative 9th.
Okay, gotcha. Thank you. Let's see. 9.67 times. See. Yes.
Nice. Yeah, so this module, Unit 2 Module 1 is a lot of math as well. But it's not bad.
Excuse me. Yeah, so on these exams, it's still going to have more math in there?
Yeah, he'll have some math questions, but he'll also have lots of conceptual questions, like story problems.
Story problem?
Where you have to know how to set up the problem and then know how to solve the math.
Okay, I see. What? There's one that's tricky.
To estimate the wavelength of the least energetic electromagnetic radiation that excites your two molecules to different vibrational state. Ooh, okay, the least energetic radiation. So we want the lowest energy. Okay.
Lowest energy. So does that have like the information in there?
Yeah, we'll have to click there. It will take us to a little I don't know, figure, yeah.
Whoa.
Okay, so this is, what do they call these graphs? I can't remember. They're not IR, UV, absorption spectra. Yeah, so these wave numbers, that's kind of like your wavelength.
Mm-hmm.
And these dips, that's where the molecule absorbs that particular wavelength. So this molecule, if you move this little slider to right about here, it should start vibrating when it hits a wavelength.
Here?
Yeah. So let's see. Yeah, so it starts vibrating.
Wow.
So at this wavelength and at this wavelength, the molecule will start to move.
Okay.
Yeah.
Whoa.
So what we have to determine is which one of those is the least energetic. So it helps, well, it helps to kind of look at this table right here, or this chart.
Mm-hmm.
So gamma rays, they have the most energy,
Yeah.
and you'll notice they have the smallest wavelength.
Mm-hmm.
So the smaller the wavelength, the greater the energy. As the wavelength increases, so now the wavelength is really big, you have long radio waves, they have the weakest energy. So if you want the lowest energy up here, you're going to want the largest wavelength.
Largest wavelengths will be this one?
Yeah, so we'll look at it on here. So, but the thing is that they're not showing wavelength, they're showing wave number, which is 1 over wavelength.
All right.
So really, a small wave number is equal to a larger wavelength.